All right, let's jump right into this explainer and decode the hidden mechanics of transverse waves. We're going to take some pretty dense foundational physics and translate it into a visually stunning, almost holographic journey. If you've ever looked at a vibrating guitar string or, a ripple on a pond and wondered about the invisible math governing all that motion, well, you are definitely in the right place. Here's our roadmap for today. 1. Anatomy of a wave. 2. Speed, energy, and power. 3. Superposition and interference. 4. The power of phasors. And 5. Standing waves and resonance. But before we even touch the math, I want you to just picture something for a second. Imagine a single glowing line. What happens to it when it gains energy, collides with other lines, and ultimately gets trapped in a confined space? How does it build into complex, harmonic resonance? Keep that image in the back of your mind as we go.
Section 1. Anatomy of a wave. Understanding the foundational dimensions.
First up, let's get the definition down. A transverse wave is a wave where the displacement of every oscillating string element is perpendicular to the direction of the wave's travel. So the really crucial thing to grasp here is that while the wave itself is traveling forward, say left to right along an x-axis, the string itself isn't actually moving forward. The little individual elements of the string are just moving up and down perpendicularly. It's basically an illusion of forward motion created by sequential up and down movements. Now, it's pretty easy to mix up wavelength and period, but they perfectly balance space and time. Wavelength is the spatial footprint of the wave. If you took a quick freeze-frame photograph, it's the physical distance from peak to peak. Period, on the other hand, is the temporal heartbeat. It's the exact time it takes for one full oscillation to occur at a single point. So space versus time, perfectly balanced. Section 2. Speed, energy, and power. The dynamics driving the wave. So there's literally a physical tug-of-war going on inside the string that dictates its wave speed. On one side, you've got tension, the elasticity or stretching force pulling the string taut. That makes the wave snap back faster, which increases speed. On the other side, there's linear density, which is the mass per unit length, or basically the string's sluggishness. That makes it heavier and harder to move, decreasing the speed. Ultimately, it isn't about how hard you pluck it. It's completely about the properties of the medium itself. So how exactly does this wave carry energy? Well, as it races along the string, it violently transfers both kinetic and elastic potential energy. And surprisingly, both of these peak right at the exact moment the string snaps through the center zero displacement line. Why? Because that's where it's moving the fastest, giving you maximum kinetic energy, and that's also where it's stretched the most to accommodate the wave shape, giving you maximum elastic potential energy. Conversely, both are completely zero at maximum amplitude when the string just briefly stops at the very top of the crest. And power? That's simply the average rate of this energy transmission as it travels down the line. Section 3. Superposition and interference. When waves collide. Okay, now we've reached the climax of our wave's life. You might expect some sort of complex, nonlinear disaster when waves collide, right? Do they bounce off each other? Do they just completely shatter? What actually happens when two transverse waves overlap simultaneously? The reality is actually beautifully simple, and it's guided by the principle of superposition. When several waves traverse the same medium, their net effect is simply the algebraic sum of their individual displacements. You literally just add them together mathematically. If one wave pulls the string up 2 millimeters and another pulls it down 1 millimeter, the net displacement is simply up 1 millimeter. That's it. Depending on their phase shift, meaning how perfectly their peaks and valleys align, these waves can do drastically different things. If they're exactly in phase with peaks perfectly aligned, you get fully constructive interference. The amplitudes just add right up, doubling in size like a massive glowing surge. But if they're exactly out of phase, with the peak of one perfectly aligning with the valley of another, you get fully destructive interference. They completely cancel each other out, leaving a flat, dark line of zero amplitude. The crazy part? The energy is still there, it's just hiding in the math. Section 4. The power of phasors. A visual solution to messy math. Now, adding identical waves is a breeze, but adding waves with different amplitudes or complex phase shifts using trigonometry, that is an absolute nightmare. So physicists use this really slick visual trick called phasors. Step 1. You just draw vectors with lengths equal to the wave amplitudes. Step 2. You imagine them rotating around an origin at an angular speed equal to the wave's frequency. Step 3. To combine the waves, you just add these vectors together, tip to tail, just like simple geometry, to find the resultant wave. It's like we treat the waves like rotating radar sweeps. The projection of that rotating vector on the vertical axis perfectly maps out the wave's displacement. It takes incredibly complex interference and makes it beautifully visual.
Section 5. Standing waves and resonance. Trapping motion into beautiful patterns.
When a wave hits a fixed end, it bounces, it reflects back. When you have identical waves traveling in opposite directions, one going left, one going right, and they continuously overlap, you get what we call a standing wave. It's an oscillation mode with fixed nodes, which are basically dead spots of zero displacement that never move, and antinodes, which are the spots of maximum wild bouncing displacement. At certain frequencies, it's like the wave forgets how to travel and just pulses right in place. This creates the absolute simplest resonant pattern, the fundamental mode, also known as the first harmonic. You have a node at each fixed end and a single, massive antinode loop right in the middle. At this specific resonant frequency, exactly half a wavelength fits perfectly on the string. Now, bump up the oscillation frequency to exactly twice that of the fundamental, and boom, we hit the second harmonic. The math actually forces the pattern to pinch right in the middle, creating a dead still node in the exact center, while two distinct antinodes vibrate wildly on either side. A full wavelength now fits perfectly on the string. Moving up again, we hit the third harmonic. The pattern subdivides once more into 3 distinct oscillating loops. And this really shows how specific resonant frequencies mathematically lock the string into higher integer multiples. You can't get 2.5 loops on a fixed string. It's got to be a whole number, like 1, 2, or 3, determined entirely by the length of the string and the wave's speed. The crucial takeaway here is summed up so perfectly by this quote. If the frequency is in the audible range, you can hear the shape of the string. Think about it. When you pluck a guitar string, you aren't just magically making a sound. You're initiating these exact harmonic nodes and antinodes. The distinct pitch you hear is literally the sound of these standing wave patterns vibrating the air molecules around them. The physics of the string is literally shaping the music we hear. How cool is that? I'll leave you with this provocative thought as we wrap up. We've been looking at 1D wave resonance on a simple string. But how might these invisible, vibrating standing waves scale up to our massive 3D real world? How might these exact same principles of nodes, antinodes, and resonance silently dictate the wind-induced swaying and twisting of the very skyscrapers we live and work in? Think about that the next time you feel a tall building swaying in the wind.